Hello everyone. In this lecture of the probability theory course, we will be talking about continuous probability distributions. We will be talking about two very specific probability distributions which appear in many problems in real life, and these are the exponential distribution and the Gaussian distribution. Let's start with the exponential distribution. The exponential distribution is related to the Poisson distribution. Recall that the Poisson distribution was the number of events that occur per unit time. The exponential distribution is defined for a random variable which denotes the time until the occurrence of the first Poisson event. In order to get the PDF of the exponential random variable, let's try to derive it from the BMF of the Poisson distribution. Recall that for the Poisson distribution, the BMF f of x was equal to e power negative lambda t power x divided by x factorial, where x was an integer starting from 0 up to infinity. Now, since the exponential random variable represents the time until the occurrence of the first events, that means that within that time no Poisson events has occurred yet. So let's start with finding the probability that no Poisson events have occurred. That's f of 0, which can be obtained through direct substitution in the previous equation for x equal to 0, and you can easily get that will be equal to e power negative lambda t. Now, this value represents the probability that no events has occurred yet, which means that the time until the occurrence of the first Poisson events has not passed yet. Let's think of the random variable t, which represents the time until the first occurrence, which is the exponential random variable. We can hence say that the probability that this time is larger than or equal t is the same as the probability that 0 events has occurred so far. So again, the probability that the time needed for the first occurrence is larger than or equal t is the same as the probability that within time t 0 occurrences has happened, which is, as we derived in the previous step, is e power negative lambda t. Consequently, we can say that the probability that t is less than or equal small t, which means that the probability that the time to the first occurrence is less than or equal small t, that is the complementary event, which is 1 minus probability that t is larger than or equal small t, which is 1 minus e power negative lambda t. It can be easily noted that this expression represents the CDF of the random variable t. Consequently, if we want to find the BDF, we need to find the derivative of the CDF with respect to the random variable t, which means that the probability density function is the derivative with respect to t for 1 minus e power negative lambda t, that is equal to the derivative of 1 is equal to 0, and then we have the derivative of the exponential. We get negative lambda, which cancels with the negative, and we get lambda e power negative lambda t, which results in the PDF of the exponential random variable, which is given as f of t equals lambda e power negative lambda t as we derived. And as we used, that is denoted as the random variable t follows the distribution, which is exponential and has a parameter lambda. Of course, it makes sense that the parameter of the exponential distribution is the same as the parameter of the Poisson distribution, since they are both related. So again, the Poisson random variable represents the number of occurrences within time t, while the exponential random variable denotes the time until the occurrence of the first Poisson event. So both of them are dependent on the parameter lambda, which represents the average number of events within time t. So as we used, if we want to verify the validity of the distribution and to find the mean, the variance, and the moment generating function of the distribution, we treat the random variable as we did with all the previous random variables. So let's start with validating the distribution. That means that we want to prove that the integral of f of t dt equals to 1. Of course, since t is a continuous random variable, then the total probability is obtained through integration rather than summation. And the limits of the integral here are deduced from the range of t, which is from 0 to infinity. So that is the integral of lambda e power negative lambda t dt from 0 to infinity, which is a very easy integral. It is lambda e power negative lambda t divided by negative lambda and substitute from 0 to infinity, which of course after substitution results in 1. Similarly, if we want to get the mean, so it is equal to the expected value of the random variable t, which is the integral of f of x for x ranges from 0 to infinity, and the same for the variance. After derivation, you can find that the mean is equal to 1 over lambda, and the variance equals 1 over lambda squared. Of course, that makes sense because the mean here represents the average time or the expected time to the occurrence of the first event, and it is equal to 1 over the average rate of occurrences of the events in unit time interval. Similarly, sigma squared can be derived as 1 over lambda squared. For the moment generating function, it will be much easier because we want to calculate expected value for e power. We used to write it as e power xt, meaning that x is the random variable and t is the arbitrary parameter. But since for this random variable we chose the symbol t since it represents time, so in order to avoid confusion, so we put the random variable t and we use any other arbitrary symbol to represent the parameter of the moment generating function, for example k, and hence this is equal to expect the integral of e power tk for multiplied by f of t, where f of t equals lambda e power negative lambda t. Of course, this one should be small t dt, which is again a very simple integral because it's for an exponential term, and it is equal to lambda over lambda minus k on condition that lambda is larger than k. And from this expression of the moment generating function, we can derive the first moment and the second moment, which can be used to get the mean and the variance. But notice here that when we use this moment generating function to get the first moment, we have to differentiate with respect to the parameter of this moment generating function, which is k in this case. So if you find the derivative of this moment generating function once with respect to k and then substitute for k equal to 0, you get the mean, which is 1 over lambda. Similarly, you can get the variance, which is equal to 1 over lambda squared. Let's solve this example together. In this example, a large corporate computer network user logins to the system can be modeled as Poisson process with a mean of 30 logons per hour. So this number represents the mean of a Poisson process, which means this is lambda, and it is defined as 30 logons per hour. Then he will be asking about few probabilities. The first of those is, what is the probability that there are no log-ons in an interval of 6 minutes? So in order to solve this, we can either consider the problem as a problem of a Poisson distribution, and we want to find the probability that we have 0 occurrences, but that will be in an interval of 6 minutes. So we have to modify our rate to be lambda t, which is 30 occurrences per hour. However, our time is 6 minutes, so that is 6 divided by 60, which is equal to 3 log-ons per 6 minutes. So that's 3 log-ons per 6 minutes. And hence, we want to find the probability that there are 0 log-ons. So this is the probability that x equal to 0, which is e power negative lambda t power 0 over 0 factorial. Again, this is 1, this is 1, and hence we get e power negative 3. So this is the probability as obtained by approaching this part of the problem as a Poisson distribution. Another solution is to use or to solve it assuming or considering the time as our exponential random variable, and we can hence say that we have an exponential distribution whose lambda is equal to 30 occurrences per hour, and we want to find the probability that the first occurrence is beyond 6 minutes. That is the meaning of having no log-ons in an interval of 6 minutes. So again, our lambda is 30 log-ons per hour, and we want to find the probability that the first occurrence is larger than 6 minutes. So this is the probability that our exponential random variable t is larger than or equal 6 minutes. And as we derived before, the CDF was equal 1 minus e power negative lambda t, and consequently this complementary CDF is e bar negative lambda t, in which we substitute for lambda as 30. However, our time, which is 66 minutes, should be represented in hours, so that is 6/60, and as expected we also get e bar negative 3. So this part of the problem can be approached as either a Poisson random variable or an exponential random variable, and if we do both of them correctly, of course we get the same result. The second requirement was to find the probability that there are 5 log-ons in an interval of 6 minutes. So this part is easier solved as a Poisson random variable. So as we did in the previous part of the question, we assume that the number of occurrences within our window of 6 minutes is a Poisson random variable, and its lambda t was equal to 3, and hence the probability that we have 5 log-ons is equal to e bar negative lambda t for lambda t power 5/5 factorial. So just by substitution, that is e bar negative 3 power 5 divided by 5 factorial. Of course, as a double check, you need to make sure that this number is less than 1. The next requirement is to find the probability that the time until the next login is between 2 and 3 minutes. So since he is asking about time, hence we will be using the exponential random variable, and as we said, t as an exponential random variable has a parameter of lambda, and this lambda is either 30, assuming that our unit time is hour, or it can be modified to be half if we consider our unit time as minutes. Of course, since the numbers given are given in minutes, it is better to use the average rate of occurrence per minute, and hence we consider that t is an exponential random variable with average rate of half. The requirement is the probability that the time to the next login is between 2 and 3 minutes. So this is the CDF at 3 minus the CDF at 2. Recall that the CDF at any time t for the exponential random variable was given as 1 minus e bar negative lambda t. Hence, this can be obtained as 1 minus e bar negative 3/2 minus 1 minus e bar negative 2/2. Of course, we substitute 3 times lambda, which is half, and here 2 times lambda, which is half, and this is equal to e bar negative 1 minus e bar negative 1.5. The next requirement is to determine the interval of time such that the probability that no log-ons occur in this interval is 0.9. So this is as if we are looking for the time t dash such that within this time there is no occurrence, which means that the probability that the time, or it means that the time until the first occurrence is larger than this t dash. So this is probability that the time to the first occurrence is larger than or equal this t dash, and we want this probability to be equal to 0.9. Again, this is the complementary CDF, or 1 minus the CDF, which is e power negative lambda t dash, that's equal to 0.9, or e power negative half t dash is equal to 0.9. In order to get that, to get the t dash, we get the logarithm of both sides, so that is negative half t dash equals ln of 0.9, from which we can calculate t dash. The next requirement is as follows. He says that if no log-ons occurred during the last 10 minutes. So now he is giving us some knowledge or some condition that we know that no log-ons occurred during the last 10 minutes. Then what is the probability that the next log-n occurs within the coming 3 minutes? So it is very important to be able to translate this wording into the right expression. So we are looking for the probability that given that no log-ons occurred during the first 10 minutes, that means that up until 10 minutes, the first occurrence didn't happen. So that means that time to the first event is larger than 10. So this is the given condition or the known information. Then what is the probability that the next log-n occurs within the coming 3 minutes? That means that the first event happens at time less than or equal 13. So that is the 10 known minutes that no log-on happened plus the 3 coming minutes. Of course, this can be calculated using the conditional probability, as this is the joint probability. So it is the probability that t is larger than 10 and less than 13. So that is t is between 10 and 13 divided by the probability of the condition. This can be expressed as the CDF at 13 minus the CDF at 10 divided by 1 minus the CDF at 10. Again, by direct substitution, knowing that f of t is equal to 1 minus e power negative lambda t. So substituting here, that will be e power negative 10 over 2 minus e power negative 13 over 2 divided by e power negative 10 over 2. By simplification, that will be equal to 1 minus e power negative 3 over 2. If someone notices, this is the same expression as f of 3. So knowing that no log-ons happened within 10 minutes, the probability that it happens in the next 3 minutes is the same as if we assume that the first of our time consideration is starting from those 10 minutes. So again, the probability that the first event happens within the next 3 minutes, knowing that it didn't happen before, is not changed by the fact of the change of the time origin. This is called the memoryless property. So the memoryless property is a property of the exponential distribution, and it means that the probability that the time to the first occurrence is less than or equal t plus m, given that it is already larger than t, is actually the same as the probability that t is less than m. That implicitly implies that the change of the time origin, if we know that up until certain time, for example 10 seconds, the first occurrence or the first event didn't happen, that means that we can ignore those previous 10 seconds or 10 minutes or whatever the time, and assume that now is the start of the time, and the probability of the first occurrence happening within the next 3 minutes is the probability that the random variable is less than 3. Of course, if we want to prove this memoryless property of the exponential distribution, we can do exactly as we did in solving the previous part. So we can translate this using the conditional probability. So this will be equal to the probability that t is larger than small t and t is less than t plus m, divided by probability that t is larger than small t. This is equal to the probability that the time is less than small t, larger than t and less than t plus m, divided by the probability that t is larger than small t. Again, by substituting using the expressions of the CDF, that will be f of t plus m minus f of t divided by f of t, and knowing that the CDF is 1 minus e bar negative lambda t, hence we can write e minus e bar negative lambda t plus m minus 1 minus e bar negative lambda t divided by 1 minus e bar negative lambda t. Those ones can be cancelled together, and we can get e bar negative here we had 1 minus, it should have been 1 minus f of t, which means 1 minus this value. So we have in the denominator e bar negative lambda t. So if we get e bar negative lambda t as a common factor and cancel with the denominator, we get 1 minus e bar negative lambda m, which is the CDF or f of m, which is again probability that t is less than m. Our next example is about the lifetime of a mechanical assembly in a vibration test, which is exponentially distributed with a mean of 400 hours. Recall that the exponential random variable has a mean of 1 over lambda, which means this is the 400, and consequently our lambda is 1 over 400 occurrences per hour. The first requirement is about what is the probability that an assembly fails in less than 100 hours. Again, fails, that means that the lifetime is reached in less than 100 hours. So again, this is an exponential random variable, and we are looking for the probability that that random variable or the lifetime or the first occurrence of the event is less than 100 hours. So this is the CDF at 100, and since the CDF f of t is equal to 1 minus e bar negative lambda t, then by substituting here it is 1 minus e bar negative lambda, which is 1 over 400 times the time, which is 100. So again, this is 1 minus e bar negative 1 over 4. The part B is, if 10 assemblies are tested, what is the probability that at least one assembly fails in less than 100 hours? This is, as we used before, this is mixing different random variables together in the problem. If we have 10 assemblies, so what is the probability that at least one of them fails within the 100 hours? So this is a binomial experiment in which we run it 10 times, and the probability of success is the probability that we just obtained in the first part, and we are looking for the probability that at least one assembly fails, which means the probability that x is larger than or equal 1, and it can be obtained as we used before. The next distribution is the Gaussian distribution, or sometimes we refer to it as the normal distribution. The normal distribution is one of the most popular distributions that appear in many natural phenomena. That's why it is one of the most common distributions for continuous random variables. The Gaussian distribution or the normal distribution is usually defined in two parameters, which are mu and sigma, and these are the mean and the standard deviation of the random variable. So we define the random variable x that it follows the normal distribution with parameters mu and sigma, and the PDF is given with this expression where x is any real number from negative infinity to infinity. If we plot the PDF of this random variable, we have this most popular bell-shaped distribution where this peak occurs at the mean of the random variable. So as we can see here, the blue, red, and orange are examples for Gaussian distribution for which the mean is 0. That's why there is that symmetry and that peak at the mean mu, which is equal to 0, while the green one has a mean equal to -2. So the probability density function looks as shown, centered around -2. And of course the parameter sigma or sigma squared, which denotes the standard deviation, affects the width of the PDF. So for the blue one we have sigma is equal to 0.2, while as we go from the blue to the red to the orange, the sigma increases and consequently the width of the distribution increases. As we said before, the standard deviation or the variance are used to give us sense or measure of the variability. So the larger the variance, the larger the variability, and the higher the probability to find more values of the random variable, and this is obvious from the figures. Moreover, for the Gaussian or the normal distribution, the point at sigma from the mean represents the inflection point of the PDF curve. For example, if we have this is the mean and the curve looks like this bell-shaped curve, for this part of the curve it is bending upwards, while in this part of the curve it is bending downwards. This is what we call an inflection point, and it is usually at sigma from the mu. Similarly, the point at sigma plus mu represents the inflection point of the PDF curve. However, this is not of a huge interest for us. We are more interested in knowing that the sigma or the variance gives us a notation about the variability of the random variable. Also, if we want to plot the CDF, we know that the CDF, which is f of x, is the integral of the BDF for all values from negative infinity to x, which represents the area under the curve from negative infinity to any value x. And if we plot these expressions, we have CDF in this form, where for the three curves, the blue, the red, and the orange, where we had the mean equals to 0, and because this BDF is symmetric around the mean, so it makes sense that the area from negative infinity to the mean, or to 0 in this case, should be equal half the area under the curve, which is half. That's why we can see here that the CDF at x equals 0 is equal to half. For the green one, it is equal to half at the mean, which is -2. And of course, it is, as we said before, it's an increasing function or a non-decreasing function with minimum value of 0 at negative infinity, and it saturates at 1, or it sums up to 1 at infinity for this distribution. In order to verify the validity of this distribution and to find the mean and the variance and the moment generating function, we need to solve the regular integrals, and you are encouraged to do so by yourself. Of course, in order to find the mean and the variance, you should expect that the mean will be equal to mu and the variance will be equal to sigma squared, which are the values which appear here in the definition of the BDF. One of the most popular normal distributions, or the Gaussian distribution, is what we call the standard normal distribution. The standard normal distribution is a normal distribution whose mean is equal to 0 and its variance is equal to 1. This is what we call the standard normal distribution. This here shows what is called the Galton Board, and it is used to show that the Gaussian distribution appears in many natural phenomena. As you can see here, the random path that those metallic balls choose to follow results in what we call the Gaussian or the normal distribution. Of course, the larger the number of the balls, the better the Gaussian distribution we see. If we want to calculate the area under the curve of the Gaussian distribution, we define this area as the integral of the BDF, and if we choose the limits of this area to be from negative infinity to an arbitrary value x, this is what we know as the CDF. This CDF is given by many names. It can be given as z of x or phi of x or q of x. Here we will adopt the notation phi of x, and as you can see, this phi of x increases with x with value equal half at the mean of the distribution, and it saturates at 1 at infinity. In order to calculate this, the area under the curve, we need to do the integral of the BDF, which is integral from negative infinity to x for f of x, which is again 1 over square root 2 pi sigma squared e bar negative 1 over 2 sigma squared for x minus mu squared dx. And this integral is not easy. So one of the most commonly accepted methods to calculate this integral is to use integral tables, so that at given values of x, you know what is the value of this integral. So again, this is what we call phi of x. However, since this random variable is function of mu and sigma, then we will need an infinite number of tables in order to define the possible values of phi of x at given parameters mu and sigma. So instead, we define phi of x only for the standard normal distribution, which again has mu equal to 0 and sigma equal to 1. And for any other random distribution which has Gaussian distribution, we transform it into a standard one in order to get the CDF, or the area under the curve, in a certain range of values. And this transformation is given as follows. If we have in general a random variable x which follows Gaussian distribution with mean mu and standard deviation sigma, and we subtract from this random variable mu and divide it by sigma, the resulting random variable z is standard normal distribution. So any Gaussian distribution with mean mu and variance sigma squared can be transformed into standard Gaussian distribution by subtracting mu and dividing the result by sigma. And we will see such effect, or how it is very easy to use such a transformation, in the following examples. However, before we proceed with the examples, let's learn how to use the tables given for the CDF. Again, if we transform any random variable to the standard random variable z, then the area under the BDF curve from negative infinity to an arbitrary parameter z naught is given in this table. So for example, if we want to find f of 0.53, so this is the probability that x is less than or equal 0.53. So this is the area under the curve for the whole range from negative infinity up until the value 0.53. So we have the values written in this table. However, in order to have good precision, we have the columns to represent the first decimal point and the rows to represent the second decimal point. So the value 0.53 can be obtained from the intersection of this row, which starts with 0.5, and this column, which is 0.03, and hence the intersection of this row and column is 0.7019. So the value of the CDF at 0.53, or the probability that x is less than 0.53, is 0.7019 from the table. However, you can see here that in the table there are no negative values for z. The values of z start from 0, so that is 0 with 0, that is 0, and as you expect, the CDF is equal to 0.5, because if we are evaluating the CDF at this 0, so the area under the curve is equal to 0.5, or half the total area. So what about if we want to calculate the CDF for some value which is negative, or some value which is lower than the mean? From the symmetry of the distribution, the area under the curve, the shaded area here, is similar to this shaded area. However, this shaded area is equal to 1 minus phi of z. So phi of negative z can be proven to be equal to 1 minus phi of z, as it is written in this expression. So if we want to get phi of negative 0.53, 0.53, so it is actually equal to 1 minus phi of 0.53. Then this value can be calculated from the table, and as we calculated previous, it's 0.7019, and hence we can calculate the required CDF. Let's solve these examples and see how to use the tables and how to do the transformation to the standard random variables. This problem says that in an industrial process, the diameter of a ball bearing is an important component part. The buyer sets specifications on the diameter to be 3 centimeters plus or minus 0.01 centimeters. So it is required that the diameter is 3 centimeters, and if there is some change, it shouldn't be more than 0.01 centimeters added or subtracted. It is known that the diameter of ball bearing has a normal distribution with mean equal to 3 centimeters and standard deviation equal to 0.05 centimeters. So now we can define a random variable, which is the diameter. We can refer to it as d or keep it x as we used to, and we know that it is normal distribution with mean of 3 centimeters and standard deviation 0.005 centimeters. Again, recall that the second parameter of the Gaussian or the normal distribution is sigma, which is the standard deviation, not the variance. The first requirement is, on average, what is the percentage of rejected ball bearings? So we want to find the probability that a ball bearing is rejected. And this is the probability that the ball bearing does not fulfill the requirement of the buyer. And these requirements are given by this condition. So we want to find the probability that a ball is accepted and then subtract this value from 1, which results in the probability that a ball is rejected. So we know that probability of rejection is equal to 1 minus probability of being accepted, and probability of being accepted is the same as the probability that x is between 3 minus 0.01 and 3 plus 0.01 as specified by the buyer. Now we want to calculate this probability. However, this probability involves the integral of the Gaussian BDF from 3 minus 0.01 to 3 plus 0.01, which is not an easy integral to calculate. So we want to use the integral tables of the phi function. However, those functions are only for the standard normal distribution or the standard normal random variable. So what we can do is that we say that this probability is equal to the probability of, and then for this inequality we subtract 3 from all 3 sides. So we get here negative 0.01 less than x minus 3 less than 0.01. And if we divide all the 3 sides by the variance, which is 0.005, so we have done nothing that changes the probability. We are just reforming the condition inside the probability, or the expression inside the probability. So this is equal to the probability, if we calculate this definition, so it is negative 2 and the upper limit is 2, and since now we changed the random variable x to be x minus mu over sigma, so we can rename this as random variable z, where z is Gaussian or normal distribution with zero mean and unity variance. This probability can be calculated as the CDF at 2 minus the CDF at -2, and both of them can be calculated using the tables. This one can be calculated by direct lookup in the table, and this one can be calculated in terms of phi of 2, which is again 1 minus phi of 2, as we mentioned in the previous slide. For the second requirement, he says that if diameters of 7 ball bearings are measured, what is the probability that exactly 2 of them will be rejected? Again, this is an example of a binomial random variable whose n is equal to 7, and the probability of success is the probability of being rejected, which we have just calculated in the previous part. One more example is, assume that in the detection of a digital signal, the background noise follows a Gaussian distribution with 0 volt as its mean and a standard deviation of 0.45 volts. So we assume that we are detecting a signal and there is unwanted noise added to this signal, but this unwanted noise is Gaussian or normal distributed with 0 mean and standard deviation equals 2.45. And he says that the system assumes a digital 1 has been transmitted when the voltage exceeds 0.9 volts. So symbol 1 is assumed if X is larger than 0.9 volts. Now let's see what are the requirements. The first requirement is about the probability of detecting digital 1 when none was sent. So if none was sent, that means that the whatever is measured is just the noise signal. So we have random variable x, which is just the noise, and it follows normal distribution with mean equal to 0 and standard deviation equals to 0.45, and we find what is the probability of detecting 1. It is the same as the probability that this measured value is larger than 0.9, and as we agreed before, in dealing with continuous random variables, it doesn't matter whether we include the equal here or we don't. And again, this is the probability that the random variable x is larger than a specific value that is normally calculated by integration of the BDF. However, as we said, the integration of the normal distribution BDF is not easy to calculate, so we do a transformation. So this is the probability that x minus 0 is larger than or equal 0.9 minus 0, so we are subtracting the mean, and then we divide by the variance, which is 0.045. So we get here, this is the probability that z, the now standard normal random variable, is larger than or equal to. So again, this is the complementary CDF, so it is equal to 1 minus phi of 2, and phi of 2 can be calculated from the standard deviation tables. So this is part A. Part B, he says that determine the symmetric bounds about the mean that include 95% of noise readings. So as if we are looking for bounds around the mean, so it is the probability that x is between two values. Let's assume them negative x naught and x naught, since they are symmetric around the mean and we have the mean is equal to 0, and we want to find the values of x naughts which makes or which result this value to be equal to 0.95. So again, using the transformation of these random variables, we can subtract the mean and divide by the variance. So this is the probability that z is between negative x naught over 0.45 and x naught over 0.45. So that is phi of x naught over 0.45 minus phi of negative x naught over 0.45. Again, this one can be evaluated as 1 minus phi of x naught over 0.45. By substitution, we can rewrite this as twice phi of x naught over 0.45 minus 1, and we want to equate this by 95, which means that after some simple mathematics, when we get this here and then divide by 2, then we can say that we are looking for the value of phi of x naught minus 45, which is equal to 0.975. So we look up in the table of the normal Gaussian CDF to find this value, and from the table we determine the argument at which the CDF equals to this value, and then equate x naught divided by 0.45 with the value obtained from the table. The last point that we want to discuss about the normal distribution is about what we call the confidence interval and the central limit theorem. Let's start with the confidence interval. It is usually common that we look for the interval of values of the random variable in which the values of the random variable is 90% probable, for example, or 95% probable, or 99% probable, and this is what we call the confidence interval. So if we are looking for the interval of 95% confidence, as we just solved in the previous example, so this interval is defined as the interval about the mean plus or minus 1.96 of the standard deviation. So if we calculate the probability that x is between mu minus almost 2 sigma and mu plus almost 2 sigma, this should be approximately equal to 0.95, which means that 0.95 of the values of the random variable x falls between mu minus 1.96 sigma and mu plus 1.96 sigma. Sometimes we are looking for a more strict confidence interval, in which we want to look for the interval in which, for example, 99% of the values of the random variable exist, or 0.999, and these intervals will be defined by mu minus another scale of sigma added or subtracted from the mu. The last remark that we want to mention about the normal distribution is what we call the central limit theorem, or the CLT. And the central limit theorem is one of the most popular theorems in probability and statistics, and it says that if we have a large number of random variables, and these random variables are added together, irrespective the nature of these random variables and the distributions of these random variables, their summation will be a new random variable, and this new random variable will be a Gaussian random variable or a normal random variable. So the central limit theorem specifies that the normal distribution is literally the normal distribution of the summation of a sufficiently large number of arbitrary random variables with arbitrary distributions. We studied the exponential random variable and its distribution, as well as the very popular and common Gaussian or normal distribution, as well as its properties.